gets them back on track. And if you get it done, that's one, the two classes that hold us up at OSU more than anything are strength of materials and dynamics in order to get into professional school. And so this really helps us out. It helps folks out a lot, yeah.
So like how it works at OSU is like let's say if you're a junior college student, you do 2 years at junior college, and you do like a normal year at OSU, and it's like you have to have like a C average, and then you can go to professional school.
Well,
it's
it's almost like a semester. You're only really short a semester.
but it's kind of like a separate entity from OSU.
Well,
But it's like at OSU.
right,
it's
well,
like-
yeah, you have to be accepted into professional school.
Okay.
But you're not behind anybody, because even though they say you can do it in 4 years, I have yet to really, to do an engineering degree and you have to have everything go just precisely correct. And you have to come in already being able to take Calc 1 your freshman semester. So those two things have to happen in order for you to finish with a engineering degree in 4 years without doing summer school.
I have a question.
Mm-hmm.
So I was thinking about this the other night. You know how like there's a lot of military academies like West Point,
Mhm.
Naval Academy, and stuff like that, and they're very well known for like their engineering and
Right.
stuff like that. And I was wondering how do they get cadets like get them a 4-year degree?
In
but
4
also-
years?
What?
In 4 years?
In 4 years? Yeah. Like how does that happen? Like do they?
Well,
do they-
first thing, you come in being able to take Calc 1 right away.
Okay.
Most people don't have the ACT score to come in and take Calc 1 right away. Because you think about what you have to do to get in Calc 1. You have to have algebra and trig. So if you can't come in with Calc 1 right away, you're already a year behind in math. 90+ % of cadets hitting the academies can do Calc 1 their first semester, or they've already done Calc 1 and they don't have to do Calc 1 at all, because they did concurrent Calc 1 their senior year in high school.
So you can like if I went to NOC, you can go to the Naval Academy and they'll accept like NOC scores.
Oh yeah, oh yeah. That's why a lot of your cadets that go in, there's a prep school. The Air Force has a prep school. The Army has a prep school. The Navy has a prep school. There are a lot of people that do a year at prep school before they start
That's
at
what
the
my
academy.
friend did.
Yeah.
I had a friend of mine in high school. His name's Nathaniel Huff. He'd get accepted, and he went to a prep school in New
Right.
Mexico for a year.
Right.
And then went to
So a lot of people do have prep school. So that's what happens. So people ask me, how did I do in my undergraduate in physics, which is just as bad as engineering, with as much chemistry as I have physics, in 3 years. I concurrent calc. So I had my calc sequence was ahead, and I went every summer. So I did 3 summers. So
I'm sorry.
I did 3 summer sessions.
How long would it have took?
4. Yeah, 4. And I was taking 18 credit hours a semester. My worst was a 19 credit hour semester that was just chemistry and physics.
I'm sorry.
So
How bad is organic chemistry?
it depends on your perspective. It did. Part of the reason I hated it is because it didn't have rhyme or reason at the time. And it was, to me, it was mostly memorization, which is another reason why I hate biology. It's mostly memorization. But once you finally understood what was driving the mechanisms, advanced organic was fun. But I didn't take advanced organic because I didn't want to. And then I always swore it was magic turtle bones anyway, because you had to deal with catalysis. And then after a while, I acquiesced and said, it's not magic turtle bones. Catalysis is magic turtle bones. So.
Is there a lot of math involved in organic chemistry, or is it just?
Organic, no. That's what drove me crazy in organic. Is that to me, organic it's all about mechanisms. And mechanisms weren't quite as mathematical. I did PChem. PChem was fun. Now, most people will tell you PChem sucks. But I love PChem, which is why I'm a chemical physicist by training. So, I mean, it's fundamental.
Is there a lot of math involved?
Oh, yeah. PChem? Yeah. You thought thermodynamics had math. Well, PChem uses thermodynamics a lot.
I haven't had those.
Thermo's fun.
Now, dynamics, one of the things for dynamics is it's primarily, if you're going chemical and biosystems, dynamics isn't quite as required. But it is on the FE exam. You can't get away from it. All right. So if I go to dynamics and I go to mastering engineering and I go to look at PACE here, as of right now for everybody, so you've got it now, we have finished through the chapter 15 quiz, section 16's 1 through 4 is done. We will finish lecturing on 17 today, which leaves us chapter 18 and 19. And just because we are running out of time, there aren't going to be any adaptive follow-ups. So your opportunity for extra credit is now getting amazingly slim. Okay? Because the last follow-up is chapter 17 adaptive follow-up. Chapter 18 and 19, I think, have like maybe one extra credit problem on it, but at this point, we just don't have time. So your extra credit, if you hadn't gotten it by now, you're probably kind of out of luck unless you've got these adaptive follow-ups that are still hanging out here. There's a chapter 16 quiz. I opted not to do a chapter 17 quiz just from a time perspective. So you've got 2 quizzes that are setting out there. And I looked at OSU's Summer Dynamics course, and OSU's Summer Dynamics course gets you through chapter 19. The 2 chapters we won't touch are expanding it to 3 dimensions. And that's just where we're at. In order to get everything, it's going to be a little tougher to get 3. We might be able to do a couple problems, but I'm following pretty much OSU's material for dynamics to cover what we have. So what we've got left is all the homework that's in there and the final. And remember, the final's worth 15% of the grade, and the final is semester. I am structuring the final to have 2/3 FE type questions on it. They may not look like they're FE type questions based on how I've done them, but there 2/3 of them would be like you would have on the FE exam. And then the other third is going to be based off of what we've had in class, what we've worked on, what you've had in homework. And basically what those FE problems are going to look like, some of them are multiple answer, but they could be easily written as a multiple choice question, which is why I'm doing it that way. So at this point, it's going to be 9 questions, right? They're going to be 9 questions, and Jeremiah, I think you're on, and Jordan, I will be emailing you guys' proctors the exams probably by tomorrow. So I should have the exam ready to go, which means for you guys, if you wanted to take it on Wednesday, that's fine with me. I just need to have it scanned in so that I can grade it and get grades in by close of business on Thursday. And which just means I have to have it before I show up Friday morning, essentially is what that means. Okay?
Have it graded.
So I can have it, so I can grade it, so I can put the grades in by Monday.
So you'll have it. All our grades will be in by Monday.
And that's my plan.
Okay.
That's my plan, because I start 2 new classes on Monday. I don't want these two classes hanging over me on that time. So, I mean, it's, you know, you guys are taking extra classes. I'm teaching 2 more classes, and luckily for me, it's chemistry and engineering physics, but
Well, that's easy stuff.
easy stuff. Well, chemistry is a lot easier because I'm just teaching it now, so it's just start over and repeat. So does that answer your question on pace? Okay, because we will finish chapter 17 today, and that gets us chapter 18. I'm not quite sure. I'm starting to do 18, and my notes for 18 are a little wonky.
I was going to ask, whenever you say 2/3 of the exam will be FE style questions, other than the fact that they're multiple choice, what do you mean by FE style questions? Like,
Well,
should
if you
we
were,
reference that?
they're like the questions we've been doing, just that they're worded like you would see on an FE exam. There's nothing, so, I mean, if you were to pick up an FE style guide or an FE practice guide, it's those kinds of types of questions. So they're broken down like the multiple choice questions that we had. So if I looked at the last test, those multiple choice questions are very similar to FE style questions.
That's the test we made.
I'm working on it right now. I will have it done by tomorrow morning.
You make it easy.
So far, it seems to be easy.
Well, that's
That means it's gonna, good luck,
Yeah.
guys.
So far, it seems to be easy.
your easy is like my.
Yeah, so far it seems to be easy, so. But of course, the questions I've written so far are stuff that we did back in weeks 1 and 2, which seem a lot easier than what we're doing now, right? All right, so we did that plate. The interesting thing about the plate problem that we did is it actually leads into what we're getting ready to start. So let's think about that plate problem that we did right before we finished up on yesterday. So I had this plate, and we had this wire, and we cut the wire, and we had the center of gravity, which would move it down, but because we had these linkages, the plate kind of goes, because it's kind of fixed, it accelerated in that direction. And we actually worked the problem by changing up, we could have worked the problem by doing a rotation, but that could have made it more complicated, right? That could definitely made it more complicated than we wanted to. We used the moments to help us out, but one of the things that we did is we looked at G, our center of gravity G, and we had the weight applied, but we said, let's work the problem where I have an acceleration that's tangent, and I had an acceleration that went in the normal direction. And we said by working in that coordinate system, my problem was a lot simpler. I didn't have to sit there and break everything down into their X and Y components. I could do it this way, and my components were broken down into my normal and tangent. So basically what this is looking like, and so this actually looks like a rotation about a fixed axis. Okay. So so if I have so I've got something that's linked, and I have a rod, right? And I could move this, so if this is actually a brake on the San Francisco trolley, which is exactly how these handbrakes work, by the way. Handbrakes on my San Francisco trolley, I'm rotating about an axis at this pin. So I can have a fixed axis. The other things that we could look at as rotations about a fixed axis is I can have a wheel, a pulley, a disc, a turntable, lots of things rotate around a fixed axis. And we can look at this by looking at a normal and a tangent type coordinates in order to help us out. So basically what happens is we can relook at our equations of motion, except instead of doing the sum of the forces in the x direction and the sum of the forces in the y direction, And if I wanted to expand this to 3 dimensions, remember I can do the sum of the forces in the z direction. So if I want to be able to do that, but now what I'm going to do is I'm actually going to look at the sum of the forces normal, and that's going to give me my mass times my acceleration of my center of mass in the normal plus my rotational acceleration. So I have my I got my translational and I have my rotational, just like what we've been doing around. Whoa. Didn't do this right. This is an equal sign. Because if I do this, I get the sum of the forces is equal to the mass times my gravitational, or center of mass has got to equal the rotational stuff about a fixed axis. Because if I have a fixed axis, this MAGN of my object, that's not going anywhere. It's on a fixed coordinate system. So I lose that piece. And so I'm dealing with this as a rotation. And then if I do the sum of the forces tangential, same thing is going to happen. And that's going to be my M alpha R G. And then my moments look like, and the moment about G, which is the point of my rotation, is going to look like I G alpha. So my fixed rotation system looks a lot better. But if I want to expand it to any point, like I want to expand it to any point along that spot, then I've got to use my kinematic items, and that looks like the distance to the center of gravity, the mass, the center of gravity, translational, plus the moment of inertia of the center of gravity and the rotational component. And this is a script M. It just smeared. And as we've seen before, a lot of the theory doesn't make a whole lot of sense, or we're drawing weird pictures to try and explain the mathematics of what's happening, but it makes a heck of a lot more sense when you start working problems. The problems really help us identify what's happening. So let's take a pulley system and let's look at it. So I got a pulley system. Okay, and off of this pulley, I've got a mass. And this is off of this pulley, I have a mass, and this is a 10-pound weight. This radius is 10 inches. This radius is 6 inches. The mass of the pulley we can't neglect, and it is so we're going to have a flywheel, and this time they're going to give us our radius of gyration of the system as being 8 inches. We're making an assumption. There's little to no friction. And we want to find the acceleration of the pulley. And this is A, and this one's B. What we want to do, all right, the first thing that we want to do is kind of make some predictions of how this thing is going to rotate. Now, since this is 10 pounds and this is 5 pounds, we have a pretty good idea, right? This one weighs more than that one. The question is, the lever arms are different, so do I have something associated with the lever arms that's going to cause me a problem? I can make an assumption that my rotation is going to go that way. And if I make that assumption, negative alpha, guess what it tells me? It tells me that my assumption was wrong. There's also a way to verify, and what I can do is say, well, if I look at the system, which I happen to know is going to be right around there, right? That's where our G is. I can look at that, and I could find the weight of B to make this an equilibrium. So this is a way to sit there and say, all right, before I get started, can I actually figure me, and I can actually do that. And if I want to do that, to have that in equilibrium, I'm going to set that equal to 0. And this analysis is called the nature of the motion analysis. Which I think is a really good tool to have in your back pocket. I'm not sure that our text actually articulates this very, very well. So I'm going to use the nature of the motion analysis, and I'm going to use this to do that. So if I did that, the weight of B acting around this part here, right, it's going to be 6 inches, minus the weight of A acting at its lever arm has to equal 0. Solve for the weight of B, and that's going to give me my 50 divided by 6, and that actually tells me that it's going to be 8.33 pounds. So if this is if this were to sit in equilibrium, B would have to be 8.33 pounds, and if B is greater than 8.33 pounds, then my picture is okay. And this helps me articulate what my picture is going to look like, and it helps me look at the motion for when I do the analysis. So now, if my motion is okay, I've got alpha going in this direction. My acceleration of A is just going to be RA alpha. And my acceleration to B is going to be RB alpha. And if I want to have this in feet, I'm going to have 10 inches divided by 12 alpha. And this one is going to be 6 divided by 12 alpha. This is going to be going, A is going to be going up, B is going to be going down. So that's my 6 divided by 12, that's my 10 divided by 12, that part's there. The other thing that makes this problem a little simpler is my IG is just going to be my mass times my radius of gyration. They gave us a radius of gyration. My mass is going to be the weight divided by gravity times the radius of gyration. So this is just going to be 12 divided by 32.2 gives me my mass. They gave me the radius of gyration, which was 8 inches, but I want it in feet, so I got to square that, and this gives me 0.1656. And if we look at the units, this could be pound, feet, squared. There's seconds, and this is feet cancels. So I get pound, feet, second squared. You'll see that as a unit a lot for I versus our slug feet squared. These are equivalent units, but it just depends on which way you're looking at it. And I wanted to introduce that because you may see this on an FE type exam, and our book goes ahead and does it like this. So you just have to kind of keep it straight. But those are the same type of units.
So why did we use just the mass of the pulley and didn't add
Because what's rotating? Just the pulley. So now, if we look at the moment about G, which is going to be our effective moment that we're playing with, okay? I'm going to have my 10-pound mass acting. I'm changing my units, so that's where that comes in. So that's this is my force distance, right? The other one's going the other direction, so that's my force distance. So this would be the mass acceleration diagram part, right? That's going to equal I alpha plus MD plus MAAD. We solve for this I. And this gives me 0.1656 alpha plus 10, 32.2, 6, 12, alpha, 6, 12. Because we solved for A, B before. Plus a minus 5, 32.2, 10, 12, alpha, 10, 12. So you get this equation, and you can solve for alpha. Right? I can solve for alpha because that's the only variable in that equation. If I do that, it works out to be 2.37 radians per second. This is weird, yeah. Then I just plug it back to solve for A, and I plug it back to solve for B, and this gives me 1.978 feet per second squared, and this gives me 1.187 feet per second squared. And we know that A is going up, so this is A is going down, AB, and my alpha is going in that direction. So you got a lot of ugly arithmetic, but the problem is pretty straightforward. So those were the three answers that you get. So let's look at another one. This one happens to be problem 1761. We have a massive cable reel. This is 1 meter in radius. And if you think about this as being a wire spool, like what they use to put lines in, we're going to be pulling off with a force of 100 newtons. The inner radius is 0.75. This is 1 meter, not 0.1 meter, okay? And that's 0.75 meters. If I'm pulling my cable off this way, I'm going to get a rotation this way. This system is 300 kilograms in mass. It's on some rollers to allow for this to unroll. And it's set such that these are equal angles, and that happens to be 20 degrees. Turns out we don't need that information. I'm sure it's in there for a different problem, but our diagram did provide it for us. We're going to call this A, and we're going to call this B. Here's where it got our axis around our location G. We're also given, yes sir, what can I do for you? Sure do. This one right there. Yeah, Fred must not be here today. So we're going to get a rotation alpha in that direction. We're given that the radius of gyration in this case is 0.6 meters. And we want to find alpha. Well, if I do my moment about the origin, that's just going to be I alpha. And this moment G here is just going to be my force, which is 100 newtons. And it's 0.75 meters.
Thank you, ma'am.
You are welcome. Not a problem. 5 meters. Now, if I'm doing this, one of the things I have to worry about is direction. But I can do this a couple of ways, right? I can do this a couple of ways. One is I can be taking that G is a negative 0.75 meters away from my 100 newtons. Particularly if I say alpha is negative in that respect, then this is going to have to be a minus I alpha. Because I want to have my alpha end up being in the correct unit. So I've got to have, there's my easy part. Well, I don't know I and I don't know alpha, but I can get I real quick because they gave me this. So remember that K is equal to the square root of I divided by the mass. So mass times K squared is going to equal I, which is going to be my 300 kilograms times my 0.6 squared, which is going to give me 108 kilogram meters squared. So I plug that into there, can get rid of the negatives. So I end up with 100 times 0.75 is equal to I alpha, which is equal to 108 alpha. So I get 100 divided by, I said 100 and I wrote 108. 100 times 0.75 is equal to alpha, and alpha ends up being 0.694 radians per second squared. It's just that easy. Now, a lot of these, it's analyzing the problem to figure out what we're doing. So this happens to be 1772. We've got a system here that's connected. I've got a wheel connected. And I've got a point that's moving without slipping kind of thing. So this is point C, so I'm going to have a normal force C. I've got an angled rod here, okay? This distance is 0.5 meters. This distance is 0.5 meters. This is location A. We're told that I'm rotating this disc at an angular velocity of 125 radians per second. The radius is 0.3 meters. I'm going to use the center as B. We're given that the disc has a mass of 30 kilograms. There's a coefficient of friction of 0.5. We're starting at 125 radians per second. We've got a coefficient of friction. We wanted to determine the time it takes it to stop. And we want to find the force at A. So the force at A, so let's look at where the force is going to happen. So this is a fixed object. Okay, so I've got a fixed object. So I'm going to have a force from my wheel. That force has got to be equal, but so these two forces have to be equal, and this is the force AC. But then, if I have a force AC, I'm going to actually have a force AY, and I've got a force AX. And one of the reasons I know that force AC, these two forces AC have to be the same, is this wheel is not going left or right because it's fixed to this position. So I'm not going to, so that portion is in equilibrium. So even though I'm worried about the forces at this bracket here, it has to be balancing out the force here from our equilibrium conditions. So the first thing I want to do is I'm probably going to need I's because I got rotation. This is I of a disk, so I can go look it up. It's mr squared 2, just from my tables, my end papers, whatever. So I can put this in. I'm going to do my 30, and I've got my 0.2. This is going to give me 1.35 kilogram meters squared. Have in the system, the force that's going to force me to stop is my frictional force at C. And we know my frictional force at C is just going to be my coefficient of friction times my normal force at C. So now let's look at my wheel here. I've got the weight mg going down. I have my force that I have to worry about. This is my force AC. I've got a force due to friction, and I have a normal force. Because this is 0.5 and that's 0.5, we know that this is a 45-degree angle. Even though they don't give it to us in the problem, they did. So I got a 45-degree angle. So now I can do the sum of the forces, mass times acceleration in the x direction. It's got to equal the force due to friction at C minus FABX. But because I'm not going anywhere in the x direction, that's got to equal 0. Same thing for the forces in the y direction. I'm not going up or down, so it's going to go away. That's going to be the normal force in the c direction minus the weight of the disk minus my FABY. So my force due to friction C has got to equal FABX. that's got to equal mu NC. So I'm going to end up with 0.5 NC minus FAB cosine of 45 degrees is equal to 0. So that's one equation. Then I get NC minus the 30 kilograms times 9.81 minus FAB sine of 45 degrees has got to equal 0. That's equation 2. We can solve those equations, pick away. You can do them simultaneously. You can do a substitution. You can do whatever way you want to. You get NC is equal to 588.6 newtons, and FAB is equal to 4162 newtons. I can do the moment about B is just going to be I alpha. But that's also going to be the force due to friction times its distance away. So I can solve for alpha, and alpha just becomes 65.4 radians per second squared. I can now solve for FABX and FABY. Just do the cosine and the sine of 45 degrees. And because it's 45 degrees, AX is equal to AY, which is equal to 294 newtons. Now to do time, I'm going to do omega initial plus alpha t, which is why I had to find alpha. I get omega minus omega initial. Alpha is equal to time. I end up with a negative 125 divided by a negative 65.4, because if this is positive, alpha actually is going in the other direction, or alpha is actually, yeah, it's clockwise, and I gotta have it go that way. And I end up with 191 seconds. No, alpha actually is in this direction because we're slowing down. This is the way we started, but the acceleration is a deceleration, so it's going opposite. But if we start with omega being positive, I have to flip the sign around.
What's that 1.1?
1.19 or 1.91 seconds. So we can expand to general motion, just like what we've been doing, but there is another special case, all right? We do have another special case, and that's when motion without slipping. And this can give us another moment equation. And that's where we get an extra moment equation. And this helps us find a point where we can kind of convert everything to motion around a fixed axis. So we're going to do a couple of problems to help us out on this. And look at a couple of classic examples, and that will get us through the rest of chapter 17. So I've got an inclined plane. And in this case, it's going to be 30 degrees. And I have a ball, and it's got radius r, mass we're just gonna use the weight. We're gonna use, it has a weight, W, it has a radius, R. It's released such that the initial velocity is equal to 0. Okay? And we're gonna look at two different cases. We're gonna look at rolling without slipping, and we're going to look at the case of just sliding down the plane. So we're going to look at both of these cases, but what we ultimately want to do is we want to determine the coefficient of friction to allow it to roll without slipping. The velocity of the center of mass after it has rolled 10 feet, and we're going to compare it to the original case that it just slides. In case first, because it's easier. The plane, and we know that mass times acceleration is just going to be mg sine of theta, because we have done this before. I don't have to worry about mass. A is equal to g sine theta, and so I'm going to get an acceleration of 16.1 feet per second squared. Then I can do the velocity is equal to the initial velocity plus AT. Or I can do, depending on what I'm after, and this is what I'm actually after. I know D, I know A, I know this initial velocity, so I can solve for V. V ends up being the square root of 322, which allows it to be 17.94 feet per second. That's if it's just sliding down the plane. Now, if I have it rolling down the plane, I have a point C that's going to stay in contact with my plane. I still have an acceleration that's going down, and I have a rotation that's occurring. If I use my C point to do this, because of that condition that I have, I can find that it's MAG, the R, okay, this is C. That's the acceleration due to gravity times the radius, plus my rotation. So now I get this point about C, doing my translational and my rotational. About C, that's the weight sine theta, that's my force, times its radius is going to equal the mass. And now this acceleration, this looks like R alpha plus I alpha. I for a sphere, if I look it up, is 2. So this is going to be 2/5 weight divided by gravity, R squared. So now I get weight sine theta R is equal to weight divided by gravity. I have R squared alpha plus 2/5 W over G R squared alpha. weights cancel out. I can solve for alpha. Alpha is going to be 5g sine theta 7r. And I can plug in for that. Then it allows me to do A is equal to R alpha. That becomes 11.50 feet per second squared. Do V squared is equal to V naught squared plus 2A change in distance. And that gives me V ends up being 15.17 feet. Then to do the coefficient of, I get my force due to friction. If the force is in the y direction, I get my normal minus weight cosine theta is equal to 0. My normal equals 0.866 the weight. Coefficient of static friction is going to be the force divided by the normal, which is going to be my 0.143 weight divided by my 0.866 weight. That's going to end up being, there it is. I wrote it down. 0.165. All right. 17.93. In this case, I've got a bar that's leaning on these two smooth surfaces. The bar has a mass of 12 kilograms. We're going to get a rotation as it starts of 2 radians per second. We wanted to turn, this is a 3-meter bar. This is 60 degrees. This is location A. This is location B. We want to determine alpha and the reactions at A and B. So let's take our bar. We know there's a center of gravity that's coming down. That's my weight. There's nothing holding it in the y direction here, so I'm just going to have a normal at B. And there's nothing in the x direction for this one, so I'm going to have a normal at A. From what we know about instantaneous centers, I can draw my lines of action, and voila, I have an IC right there. Well, from that, we can figure out some dimensions, right? Because this is a 1.5, this is a 1.5, so we'll use those dimensions. If I need to, I can figure out this one, or I can write it in the problem. I can separate this out into 2 motions. One is the weight coming down here and a rotation. And then one is dealing with the fact that this one is sliding down and this one is sliding out. Which is also, I've got my rotation. So I can actually look at 2 parts to this. I'm gonna start here. The sum of the forces in the y, in the x direction is gonna be the normal b has got to equal the mass times the acceleration of the center in the x direction. And then the sum of the forces in the y is gonna give me the normal a minus the weight is equal. Then I can do my moments. My moments, I've got the 12, 9.81, 1.5 cosine of 60 degrees. And this is about the IC, okay? So I'm doing this. It's causing me to rotate about the IC here. That's that side. And this will then go minus 12 AGX 1.5 sine of 60 degrees minus 112 AGY 1.5 cosine 60 degrees minus 9 alpha. And the 9 alpha comes from solving for IG is equal to 1/12 ml squared. I get 1/12, 3 squared is equal to 9. And that's in kilograms meters squared. That's where this 9 comes from. And if you want to look at that in terms of how that equation, mgd equals MAD plus I alpha. So if I do this, this ultimately simplifies to the following. The square root of 3 AGX plus AGY plus alpha has got to equal 9.81. AG, going back and looking at, if I look at it from B perspective, I've got the acceleration of B plus the rotation, where this is the radius GB minus omega squared RGB, and RGB is equal to minus 1.5 cosine 60 degrees in the I direction, minus 1.5 sine 60 degrees in the J direction. So I'm going to go ahead and write out all the gory details. GX in the I direction minus AGY in the J direction is going to give me, when I plug this back into here and plug all of this stuff into there and do my cross products, I end up with that this is 3 minus 0.75 square root of 3 alpha in the I direction plus 0.75 alpha minus AB plus 3 square root of 3 in the J direction. So now I get two equations. I can do the same thing about A. So I get AAB plus alpha cross BA minus omega squared RBA, where RBA is equal to minus 3 cosine 60 degrees minus 3 sine 60 degrees. And this is the j direction, that's in the I direction. You do the same analysis, and then you've got enough equations to solve for all your unknowns. And you ultimately get alpha is equal to 2.452 radians per second squared. AGX is equal to 0.1859 meters per second squared. AGY is equal to 7.0355 meters per second squared. The normal at A is 2.23 newtons, and the normal at B, oh, whoops, I'm sorry, that's normal at B. Normal at A is 33.3 newtons. And this is just mass times acceleration, GA. B is the one that's, I may have them backwards. No, I shouldn't. But you just do the mass times acceleration and get those. So it becomes some gory arithmetic, but it's not too bad. Okay, that's chapter 17. We'll start chapter 18 tomorrow.